Okay, this one is part 2. Now we go to introduce another formula for the gravitational force. The formula we related, after that we create another one. So for this one, we need to find out relationship between the gravitational acceleration. That means the G, the 9.81 you say one, that one G, on the surface of the Earth with the universal gravitational constant. So they want to find the small g and the bigger G. What is the relationship? Okay, so from here we're going to see Newton's second law of motion. Newton's second law of motion, before that we learn gravitational universal law, we just learned, so we show the formula. Okay, so this one is normally it's a F equal ma lah. Okay, but for this one situation we're using the G. Okay, gravitational acceleration. Okay, just like the gravity. Okay, this one is before that we learned Newton universal law. Okay, now I want to combine these two formula because both also talking about the force. Okay, then this one equation 1, this one equation 2. Okay, after that I put the equation 1 and 2 equal. So they become mg equal g capital M small m r squared. Okay, so from here, which one normally we can cut? Capital M we cannot cut. Capital M normally for this situation we for the more heavier object. Example, sun, earth, and also moon. Okay, so we need to related the sun with the object or related the earth with the other object. So that means M is stand for the small object. Okay, normally the capital M we never cut one. So from here we can cancel is a small m. Okay, the small m. That side is measure the small object, what is the weight. This one also is a small object mass. So after that we go to cancel the m. Then I can create the relationship small g and also capital G. Okay, but capital G you know there's a constant value. Constant value 6.67 times 10 power of 11. I forget the negative 11 or 11. You press your calculator, you can see already. Okay, there's a C over NST 39. There's a G. Okay, so the answer negative 11. Okay, so this one's a constant value. So important, they want to create this one formula. They want you to find out gravitational acceleration actually related to what? Okay, first one related with the capital M. Number 2, related with the distance between the two objects. So this one is a gravitational acceleration. Okay, so from here we see the factor. Okay, factor that will affect the gravitational acceleration. The first one factor, there's a distance between the center. Okay, you see center of the earth, they already fixed one should be the earth. Another one, object. So that's why I told you capital M we never cut. Capital M is stand for earth mass. Okay, the small m we can cut because for the object. Okay, after that this one is a R. Okay, another factor is the mass of the object. So mass of the object from here they stand for the earth lah. Okay, if I change not earth or you say sun, so the gravitational acceleration that will changes. Okay, so this one is a formula. The second formula for the universal law. So we find the gravitational acceleration G equal capital G, capital M over R still square. Okay, so we continue. Okay, relationship. Distance R increase. Gravitational acceleration G decreases. This I understand. When you just go further, the planet is go further, then I know sure the gravitational acceleration become less. Okay, example, the moon. The moon is far away from the earth. So you find it, the moon gravity is less compared to the earth. Okay, so this one is one of the relationship between the G and also the R. Okay, now we're going to see this one. Gravitational acceleration G always towards the center of the Earth. So that means they pull everywhere from the surface. You also pull towards to the center of the Earth. Okay, number 2, the value is how many for Earth? There's a 9.81. This one is normally we use it lah. The gravitational acceleration when you want to measure the, you calculate the weight. W equal mg. So you're using this one g. Okay, the direction of the gravitational acceleration is distant r from the center of the Earth. So that means if the body is in the Earth, so when they pull to the center, so this one we call it as a r. Direction is go where? Go to center. So you can see all the arrow here, direction is the same. Go to center of the Earth. So depend you how far lah. If you further, so your distance should be longer. If you're shorter, then your distance become short, and also all the direction must go to center of the Earth. And the last one, you can see the example. If the object is from here, so the force is pulling to the center of the Earth. So this one we call distance. Okay, so this one we call distance. So that means G, gravitational acceleration for the Earth, equal gravitational constant, mass, Earth mass. Okay, after that, for the R squared. Okay, so depends this one situation. Okay, for if I want to measure this point to the Earth, so we count this one, M is stand for the object. Okay, we check first. Okay, gravitational M. Okay, they got mentioned here. Explain for you what's the meaning for the M. Wait. M is stand for mass of the Earth. Yeah, small m is mass of the object. So from here, there's a mass of the Earth. Okay, the mass of the Earth is how many? Okay, so from here, okay, later you see example, then you understand. So important, we see the formula is a G capital M over R squared. Okay, then you remember the R must from the center of the object to the center of the Earth. So example like this lah. First object, second object. This one is the moon, this one is the Earth. So after that, this one is the R. Okay, when it just pull to the Earth. Okay, later we check the capital M actually is what. Okay, from here I find it. Depend the situation is how many. Okay, we never fix every time it's a Earth. Maybe got other planet. Okay, now we're going to see this one example. Okay, we take the mass, the Earth is a center, then we make the satellite further and further. We see what differences. Okay, first one, this one center. Okay, if the object is at the radius, okay, exactly the surface. Okay, after that, we need to find what is the gravitational acceleration. Then continue. If the satellite continue to move 2R, 3R, 4R. So we also need to find out what is the G. Okay, when you move different radius. Okay, so they give you the info. Mass for the Earth, then radius of the Earth, and also the gravitational constant. So from here, G equal capital G, small m over R squared. So understood this one capital M is for what? For the Earth. So that means the object you go further. So we still refer to the mass of the Earth. Okay. So from here you can try. You can try to do the calculate the value of the gravitational acceleration for the 5 distance. Okay. Complete the table below. So from here, the table I think you can no. If you don't have, we just show here. I think your paper don't have. So from here, after I do the calculation, I'm just using the formula. G equal capital G small m over R squared. So I find it when exactly there's a R, I find it there's a 9.81. Almost 812 lah. So this one is a when on the Earth surface. Okay? On the Earth surface. Okay, when they keep increasing the radius, so I find it 2.455, 1.09, then 0.6, 0.3. So from here, the conclusion I can make it when the object just further and further from the Earth, gravitational acceleration will drop. Okay, R keep increasing, so that means your G will dropping. Okay, so this one is to show different radius, what the result you can get it. Okay, I think your paper got activity 6. Later we go to answer activity 6. Okay, you refer the PowerPoint first. Later we do the paper. Okay, so this one is just now table. So I find it when the R increasing, the G dropping. So from here, the discussion is, what is the value of the gravitational acceleration on the Earth's surface? On the Earth's surface means R. So my answer just refer the table. There's a 9.819. Okay, that one is normally we take one gravitational acceleration. So that one is where exactly surface of the Earth. So when I want to plot the graph for this one table, the graph like this. Okay, this one is stand for what? When I am a R, so this one should be 9.819. Okay, after this point, you'll find it, they're dropping already. Okay, they drop 2.4, 1.0, 0.6 until 0.3. So when we plot, you find it, there's an inversely proportional graph. So from here, the first part, I can say G directly proportional with the R. Okay, because they keep increasing, pass through origin. Okay, until where? Until maximum there's a R, then stop already. So for second part is G directly proportional if 1 over R. Inversely lah. So that means if I mention about R, G inversely proportional with the R. Means when you just after R, example, 2R, 3R, 4R, then your G will drop, and drop. Okay, so before you further from the R, you still inside the Earth, your gravitational acceleration will be keep increasing until R. So example, if the Earth is here, you exactly at the center, you are no gravitational acceleration. You already at the center where God. So from this one concept, we find it when I far away a bit, this one small r, from the center, my r may be 2. Okay, but go far a bit, maybe it's 4. Okay, far a bit, maybe 8, or until surface, 9.81. So that one should be the maximum. So that means inside the Earth and far away from the Earth, the concept is different. Inside the Earth, that means you are directly proportional with the R. Okay, the distance from the center further, your G will become bigger. Until where? Until surface. So that means the surface of the Earth should be the maximum of the gravity. Okay, after that, after the R, then we need to go to the concept for this one. Okay, inversely proportional with the distance. So that's why finally they plot the graph become like this. Okay, so this one is one of the things to tell you what's the relationship, the G, and also the distance between the center of the Earth. Okay, and also this one graph is how to get it. Okay, because we do 1R, 2R until 5R, we get the result like this. Okay, second one, they call you to plot the graph, G against the R. So G against the R means G is here lah, y-axis. Okay, then this one should be R. So we find it when I just plot by using the graph paper. So this one should be 9.81. Okay, then I continue to plot. 2.4, 1.09, 0.6, 0.3. So finally, I find it. This one is an inversely proportional graph. Okay, this one is a directly proportional graph. Okay, the next part is the body is at the height from the center of the Earth. If more than R, then you understood lah. If more than R, that means you need to plus one more H. This was normally they're talking about satellite. Okay, far away from the surface. Okay, so from here, this one is a formula. before that we learned gravitational force, capital M, small m, then R plus H, then square. Okay, then this one, force equal MA, but from here I say GH lah. G is stand for gravitational acceleration for the object got height, with the height. So from here I go to explain. Equation 1 equal equation 2. So I just get GH equal capital G, small m, R plus H. You only plus one more H. Before that, we say G equal capital G M over R square, is it? But this one, you have me to add one more H. Because there's a from the surface of the earth, they're out already. So you need to plus one more H. So from here, we explain one means of GH. Okay, GH is an acceleration due to gravity at the height. They got certain height from the earth's surface. Okay, G, gravitational constant. You see the M. M normally is talking about Earth, mass of the Earth. They never mention the mass of the satellite. Okay, mass of the Earth, because we want to find is a gravitational, gravitational acceleration for the Earth. If you go further, so every time we just compare with the Earth. So we're using the capital M is for the Earth. Okay. Use something body compare with the earth. So the measure we're using the earth lah, we never using the other body. So R is stand for radius of the earth. So we create this one formula. Actually, these two formula is the same lah. Only this one is further. Then you need to plus one more H. Okay, then we go to the next part. Okay, the conclusion is the further from the Earth's surface, the smaller the gravitational acceleration. So this one is a conclusion. So when you just go to further and further from the Earth, you find that the gravitational acceleration should be dropped and also dropped. Okay, so from the graph again, we're going to see the conclusion. Okay, first, when you find the small r, that means the Earth. Okay, inside the Earth, this one we call small r. Okay, the small r is less than the radius. So G is directly proportional with the r. So we can create this one equation for part 1. Okay, when part 2, you already over the radius. Okay, radius, exactly radius as the face of the Earth. So we find the small r already more than capital R. So G is inversely proportional with the R square. Okay, R square. Okay, so from here we can get it. This one situation is, normally we didn't mention R square, yeah? We mentioned R. Because this one you're using the formula, they got square already. Okay, depend the situation. Okay, if follow the formula, memang got square lah. G capital M, then R square. Okay, if follow the graph, we're still using the R. Okay, we're still using the R. Follow equation is R square. Follow the graph is R. Okay, so this one is the formula lah. If you're using R square, this one is for the radius. So we still put the square. Okay, if for this part, there's an inversely already, then this one should be directly. If exactly surface, so you just take, normally you find the answer should be 9.81. Exactly. Okay, because there's a value is a constant. Unless you go to other distance, then we do know what is your gravitational acceleration. Okay, normally the question want you to find is a further already from the Earth. What is the G? Okay, now we're going to see some example question here. Okay, how they set the question. Okay, I think this one is in your paper. There's an example 9. You can check the example 9. Okay, we're going to see what info they provided. Okay, they want to calculate gravitational acceleration, G, of an object with the mass 50 kilogram above the surface of the Earth, given that the mass of the Earth is this one. Okay, and the radius of the Earth also provided. Okay, G also provided. So they want to find what is the gravitational acceleration. Okay, So from here, surface, surface of the Earth. So surface of the Earth, that means we're just using radius. That's enough already. Okay, one more thing you can see, be careful. We got two masses, 50 kilogram and also the mass of the Earth. Okay, some students, they will misunderstand. We need to using which one mass? Earth or also the mass of the object? Just now I told you the capital M. We need to using for the Earth. Okay, we need to using for the Earth. Okay, we write the info first. Okay, this one Earth. Okay, one more is your object lah. I forget to write. Your object is 50 kg. Okay, radius. Then after that, we got gravitational constant. So they want to find the small g. So for the chapter 3, normally the question is straightforward to the formula. Okay, you don't miss up the formula, but the formula is, they never call you to change this part, change that part. No, exactly use the formula. So we just using the formula, put in all the info. 6.67, this one is a G. This one is a mass of the Earth, not mass of the object, is Earth. Because every time we want to compare with the Earth, so we take the mass of the Earth. Okay, after that, the last one should be the radius lah. Radius of the Earth, because it says surface. Surface, so you no need to plus the H. So the straightforward take radius. After that, we go to square. So we see the answer for the G is how many? Okay, 9.81. You see exactly at the surface. Okay, so you find the answer for the gravitational acceleration. That's a 9.81. So remember, gravitational acceleration, the unit is a ms -2. Okay, so this one is every time we're using the G to do your calculation. So that means we assume all the thing is on the surface of the Earth. So this one is a 300 kg satellite orbiting around the Earth at the height. This one is a keyword. So that means the satellite is not on the surface. They got height. Okay. So given that the mass of the Earth provided, radius of the Earth also provided. So they say, what is the value of the gravitational acceleration? So we just write the info. Okay, mass of the Earth. Okay, this one is the mass of the satellite. Okay, this one is the radius of the Earth. This one is a height. Okay, height power of 3 because I want to convert kilo. Okay, this one gravitational constant. So we're still using the same formula, but you need to plus H. This one is an extra because satellite is far away from the surface. So from here, that means this one you need to do the extra work lah. So you need to press the bottom calculation first and drop down. Then you do the upper part over what you drop down, the answer. Then you get it. So I just write all the info first. G, mass of the Earth, not the satellite. Okay, every time remember this one is a ME. Okay, after that R is a radius. This one is a plus, not multiply, it's plus. 550 times 10 power 3 because kilometer. Then the whole bracket you go to square. Okay, so we do this one first. Do the bottom part first. Then you copy the answer. Then you baru go to press the upper part. Okay, upper part you equal already. Then you straightforward press divide. Divide what? Divide what you mentioned just now. You drop that one. You just divide, then you type. So from here, I get it, 8.32. So that means now the satellite, the height is a 550 kilometer from the Earth. You see the gravitational acceleration drop, become 8.32. Okay, our Earth surface 9.81. Now I see the satellite when it just launched far away from the Earth. So the gravitational pull, the acceleration, become less. Okay, this one question just same like the just now, exactly put in, but the problem is just the height. Just the height, you need to be careful. So after this one, we need to go another formula. Okay, another formula is related with the velocity. Okay, we go to centripetal force. Okay, centripetal force in the motion of the satellite and planet. So that means the satellite and the planet also moving. The shrug of velocity. So this one velocity, how come they create the velocity? They got shrug of something to pull. Then finally they can move. Okay, so from here we can see four position of the satellite which orbit around the Earth with the uniform speed. Okay, we got four satellites surrounded with the Earth. After that, they move with the uniform speed. Okay, an object in the circular motion always experience the changes direction because this one is a circle. When you move, you sure change direction one. Okay, so when you change the direction, the motion, even though the speed is a fix, although your speed is a fix, but you when you change the direction, that means your velocity changes. Okay, remember the speed is no direction. Okay, but velocity got. Okay, when I'm talking velocity, that means you cannot say, oh, the first one and the second one is the same. No, because your direction, when it's just turning the circle, you are changes. Okay, so from here they say, therefore, the velocity of the body changes. Okay, when you just, the speed is the same, when you just rotate, the direction is a different, so your velocity already changed. Okay, now we continue. A force is required. This force required for what? Required for the satellite to change the direction. Okay, you got speed, you move. If you move straight line, it's okay. But the problem now, you need to change the direction, follow the circle track. So that means the force need to help. Okay, needs to help the satellite to follow the track and change the direction. So from here, the force that act on the body, which move in the circular motion, we call it as a centripetal force. Okay, so remember this one force used for what? This one force is used for the satellite when they just want to orbit the earth, they change the direction, let them to change become smoothly. So this one force we call centripetal force. Okay, after change, the velocity can continue to move freely. So that means centripetal force is related with the velocity. Okay, not related with the mass. Got lah, a bit lah, but the important is the velocity. Okay, so now we're going to see this one centripetal force. What is the formula there? Okay, so we go to answer the question. Okay, when the rubber stopper, they make a circular motion. Okay, the stretch of the string exert the force on the rubber stopper. What is the direction of the force? Okay, the centripetal force, what is the direction? The direction sure is follow the rubber stopper, is it? Because the rubber stopper move in circular. Okay, they just follow the shape. So from here, the direction of the forces is in a direction towards the center of the earth. Okay, force is pull in. When you go anyway, they also got force to pull into the center. Okay, they're just like the tension. How about the direction? Direction is moving the whole circular. Okay, rubber stopper, moving whole circular. Centripetal force, go center of the earth. Any circular you go to turn, all the force must go to the center of the earth. So this one we call center of the earth. Okay, center of the circle. Number two, what is the relationship? Speed of the rubber stopper and the centripetal force. So that means when you swing faster, you need to hold the straw becomes stronger. Agree? So you swing very slow, that means you no need to hold stronger. If you want to swing faster, that means you need to hold it becomes stronger. So from here we find it, when the speed of the rubber stopper increase, centripetal force is increased. Okay, because you need to hold some more tightly, then prevent it fall down, is it? So you hold, when it just fast speed, that means you need to hold very strong. So this one is a centripetal force to stop the rubber stopper, tension go to the center. And the last one, how does the centripetal force change when the rubber stopper make a circular motion in smaller radius? That means I make it shorter. What do you think about the centripetal force? So from here, increase the tension of the string, so the centripetal force will be increased. If you make it become shorter and longer, that means you very take longer time to swing, and also you need to swing harder. Okay, now they say when smaller radius increase the tension. Why the smaller radius can increase the tension? Okay, anybody can tell me? When small radius, the tension is more or big? Small radius, you go to try when you do this one activity. Longer the tension you shrink. Okay, as smaller the tension you go to swing. So I just know faster lah. Faster, sure, the smaller you go to swing faster. And longer you go to swing, sure, is a longer time. Okay, but the tension for the string, how? Which one is more tight? Tight is a tension. That means longer, that means you not tight. You lose one. That means you go to swing. It's smaller, that means your string, when you pull more tightly means the tension is high. Then after that you can swing faster, although you're using the force is the same, go to swing, but the smaller the string becomes shorter, you can swing very fast. Why? Because the tension is very strong to pulling the stopper, so you can swing very fast. Okay, longer one, although you produce the same force, go to rotate, but you need to let it to move bigger circle, and the tension from the center to the stopper is less because they loose already. Closer is more tight, further they become loose. After that, when you swing, that takes some time. So from here, the question they ask you, centripetal force changes when the rubber stopper make the circular become small radius. Small radius, that means tension high. Okay, tension increase. So from here, increase the tension of the string, centripetal force also increase. So that means the force pulling from the stopper to the center increasing. So example like this, I'm going to draw center like this. Your stopper very small, then you go to swing. Okay, for this one, the tension for this one string is more strong. So if tension strong, that means the centripetal force from the object to the center also strong. Okay, and also swing faster. Okay, so this one is what they want to give you some example for the centripetal force. So that means today you can try for this one activity in your house. You can feel it. You feel by yourself, because we mentioned centripetal force, you also don't understand. What is that? I never see. Okay, so that means you can try this one activity in your house, then you go to swing. Then your hand can be feel it. How about the forces? How the string go to pull? Which one stronger? Stronger means you can feel the string is one to pull out one. That one. Which one is the weak one? So this one you can feel by yourself. Okay, when you find the string always tight to pull, that one means centripetal force very strong. Okay, when you find the string is loose one, easy to swing, that one means the centripetal force is very weak. So this one is one of the example, okay, to let you to know what is the centripetal force. Okay, then we're going to see centripetal force. What is the definition? Okay, there's a one of the force act on the body, okay, in a direction towards the center of the earth. Okay, center of the circle body lah. Okay, we say earth, there's a earth, but this one not only for earth, the something swing also can say like that. So we just say toward the center of the circle, for the body is circular motion. Okay, when it swings circular motion, there's a one of the force. on the body pull to the direction of the center. So this one we call centripetal force. So same like the what you mentioned about the tension. Okay, pull towards the center. After that, you can see when it's just moving, all the rubber stopper is moving in different velocity. Okay, so the formula for the centripetal force, there's a F equal mv square over r. M is a object M. Okay, the rubber stopper mass. V is a velocity for the rubber stopper, then square. Then R is a radius. The radius from the object to the center. Okay, so from here they explain for you centripetal force, mass, linear speed, and radius of the circle. Okay, so we can try example 3. This one is from your example 11. Okay, follow your notes. There's a 11. Okay, this one is a one example demo for the centripetal force. Okay, we see what the info they provided. Okay, rubber stopper, the mass, rotated with the radius circle. That's a R. Okay, cm. What is the centripetal force acting on the rubber stopper when the rubber stopper moving with the speed? Okay, speed is meter. So later this one you need to change lah. The radius you need to change become meter. So from here I write the info. 0.1 kg. Velocity is 10. After that, this one later you convert the R radius, make it become meter. So I want to find the centripetal force. So I just show the formula. Okay, mv square over R. So you just put in all the things. So I told you this one topic 3. They're not very hard. Important you understand the question, what info they provided. They just want to apply formula. Okay, so now you can check question 13. Example 13. Okay, example 13. Got two objects, object A and object B. Object A is the Earth. Object B rotate the Earth. Okay, now they show the object A on the surface of the Earth and the object B at the height from the Earth. Okay, object A is on the surface lah. B already far away from the Earth. Okay, then the R is the radius of the Earth. Capital R is a radius. Then the H is the extra height. Okay, after that, they're from the center of the Earth, and M is the mass of the Earth. So capital M is the mass of the Earth lah. So from here, they give you 4 different alphabet. G, gravitational constant. Capital M, mass of the Earth. R, radius of the Earth. And small h. Small h is the height, the object B from the surface of the Earth. So the first one, they want you to, based on the information above, derive the gravitational acceleration by using these 4 alphabet for the object A. So for the object A at the surface, then we just using R capital. Okay, so the answer for the object A, this one formula. Is it example 15? I think so. Example 15. Okay, this one is talking about centripetal force. So they're going to rotate. Is it? You see the diagram, then you know already. Okay, diagram show about the stone. Okay, they tell you the stone, the mass is 0.5 kg. It's tied at the end of the string and spin horizontally with the radius 30 cm and the speed provided. Okay, on the diagram, you mark an arrow direction of the centripetal force act on the stone, label with the F. Okay, centripetal force just like the tension of the string. So there is a pull to the center of the Earth. So you need to draw the arrow, go the center of the Earth, and you label this one is a F. Okay, So this one is a centripetal force. Remember, pull to the sentence. Okay, now calculate the centripetal force. Okay, we show in form. Okay, so everyone, just good night. See you next week again. Bye, everyone.